So we're going to continue on with our examination of logarithms. This is section 4.4, where we evaluate logarithms, and this is where your calculator will be used, and also introduce to you the change of base theorem. So here, this little block of text right here pretty much is telling you a definitional, a notational definition. Those are the words I want to say. So they tell you for all positive numbers x, so remember the domain of the logarithm function is the domain is all positive numbers 0 to infinity. So that's our domain. So for all positive numbers x, we denote the log of x, log of x, is the same as the log to the base 10 of x. So it's not a coincidence that we have log to the base 10, because we literally use base 10 numbers. And why do we use base 10 numbers? Probably because we have 10 fingers. It's a coincidence of nature why we favor base 10. Of course, the natural log, the log to the base e, is mathematically much more beautiful and is used quite a bit more in mathematics than log to the base 10, except perhaps in science, like astronomy and other areas of science where they're investigating natural phenomenon. And even then, of course, the more natural mathematical approach is to use the natural log rather than the log of the base 10, because literally the fact that we have 10 fingers is a coincidence of nature. So let's go ahead and take a look. Let's do these problems. So you're going to need your calculator with the log key. So I'm bringing mine up. And my calculator that I'm using here is my computer calculator, so you all can see it. And I didn't download anything special. And my particular calculator will look differently than yours. I think there might be some way that I could import into Linux the Windows calculator. It's not worth it. Notice right here I have log, log, that's log to the base 10, and ln right next to it, that's the natural log. And for this particular calculator, to find log of 1000, I literally hit it in that order, log 1000, and then I hit equal. But we're not going to hit equal just yet. Let's think about this. So we know that log to the base b of y is equal to x implies b raised to the power of x is equal to y. So in this case we have log, and here I'm going to write the base in explicitly, of 1000 is equal to x. So that means 10 to the x is equal to 1000. So let's solve this. 10 to the x, well, 1000 is 10 cubed. Since the exponentiation function is 1 to 1, that implies x is equal to 3. And indeed, when we look at our calculator and I hit the enter button, the answer is going to be 3. So let's do this next example. Let's take the log, not natural log, but log to the base 10 of 142. So let's again think about that. So the log of 10 is equal to 1. Log of 100 is equal to 2. And log of 1000 is equal to 3. So we want to find the log of 142. So I know it's going to be greater than 2 and less than 3. So that's an important lower and upper bound. I'm not for sure what it is, but I'm rather expecting that it's going to be closer to 2 than it is to 3. So let's actually find out what it is. And it turns out to be 2.152288344. As far as the rounding off at decimals, I'm not for sure. I would suggest that MyMathLab has you rounded off at the 100th place, which is the second decimal, the second place to the right of the decimal, but you just have to do whatever MyMathLab tells you to do. So here is an interesting question. So I'm going to pose it to you. So we kind of learned that log of some number y is equal to x, and we learned something about, well, maybe we did and maybe we didn't. What happens when the value of y is greater than 0 but less than 1, and what happens when y is greater than 1? Now 1,000 is greater than 1. 142 is greater than 1. But log of 0.005832 is in this range. So we know again the domain of the log function is all positive real numbers. But the range, on the other hand, minus infinity to infinity. So let's see what happens here. I'm curious what you think the answer will be. And let's take a look. So just I'm not asking what a general answer would be, but what would be an interesting characteristic of the answer, not the exact answer. Well, if you guessed it's going to be less than 0, in other words, negative, then you're right. So the log of if the value y, that we're taking the log of, is between 0 and 1, the answer is going to be less than 0. If the log of the number that we're going to be considering is greater than 1, then the answer also will be greater than 0. So let's look at some applications here. Again, all of these are going to be calculations. Calculations common, as a matter of fact, in the sciences. So many scales in science and in nature are logarithmic, including the Richter scale for earthquakes, and in chemistry, the pH of a liquid or a solution. And the pH is a measure of acidity. And this is the formula. If I know the pH, and this will be a number, so we have the formula. Let's go ahead and write that formula down because we'll want to use it. Small p, large H. I don't know what it stands for. It's equal to minus. Notice the minus here. This is log to the base 10. And over here, we have to be given the meaning of this symbol. And indeed, this tells you right here. H3O plus, the plus indicates it's an ion, it's a positive ion, is the hydronium ion concentration in moles per liter. Now these units right here, moles per liter, when you actually use calculations like this, if you're in biology or in chemistry, I think this is probably more of a chemistry problem, then those units are really important. But for right now, we're going to ignore the units and just treat them as pure numbers. So we have an example. This is question number 2. Let's do 2a. Find the pH, so the pH is my unknown, of a solution of H3 of hydronium, which is 2.5 times 10 to the 4th. So our pH is our unknown, so it's going to be equal to minus the log, log to the base 10 of 2.5 times 10 to the minus fourth. Now think about this. Let me do something here. I'm going to put the negative here. I changed its color. Now 2.5 times 10 to the minus fourth, that's a number greater than 0 but less than 1. So the log itself will be negative, and then I'm taking the negative of that, so I'm going to get a positive number. So again, bringing up your calculator, you will hit minus log, then 2.5 times 10 yx minus 4. Is that going to work? We'll see. No, it's not going to work. I don't know what I did there. Let's do this all over again. Because it should be positive. It should be positive. Well, let's break it down. Let's do as much math here. And you can probably figure this out on your own calculator. This is minus the log. Let's use logarithm rules. Minus the log of 2.5, this is multiplication, times 10 to the minus 4. So by my log rules, this is minus the log of 2.5. All of this is in parentheses. And this is multiplication here. So that's the same as the log of 10 to the minus 4. Well, that's minus the log. Sorry, I'm being schizophrenic about whether to write a capital L or a script L. 2.5 times, the minus 4 comes out, minus 4 times the log of 10. Notice how math comes to the rescue if you don't know how to do things in your calculator. And minus, I'm going to have to calculate the log of 2.5. But I know log to the base 10 of 10 is 1, so that's just minus 4. So let's do that in the calculator. That I can do. So what I will do is I will just find out what the log of 2.5 minus 4 is, and then I'll change the sign. That's by applying the negative right there. And we'll just do that in our heads. There should be a change of sign. Some calculators have change of signs. I don't see one necessarily on this one, and like I said, I don't want to mess with it because this is not about a particular calculator. So let's calculate what's in parentheses and then we'll change the sign. So I know how to find the log of 2.5, and then I'm going to subtract from it 4, and then I'm going to change its sign. So it's 3.6 approximately. And if you've done anything with pH, you know that's a perfectly normal and acceptable pH level. This little symbol I did right here, you can do it either this way, that means it's approximately equal to, or this way. Mathematically, there are distinctions. It's just somebody's preference somewhere. But I want to draw your attention that this is the exact answer. But you can't do much with an exact answer, can you? Because you don't know how much it is. You couldn't locate it on the number line. So this is the approximate answer. And you can do something with it. You can locate 3.6 on the number line. So find the hydronium ion concentration of a solution of pH 7.1. So again, we start with our formula. We're given a formula, and you will be given any such formula as needed on the exam. So you know that the exams are open notes, so the formulas are going to be there for you. So it's minus log of the H3O concentration. So in this case, we're given the pH. Minus log to the base 10, and I'm just going to call this amount here is going to be my unknown. And you can put it, you can leave it in the brackets if you want, and whatever. So what does that mean? That means we can solve this. So we're going to solve it by getting rid of this negative. I'm going to multiply both sides by negative. So minus 7, I want the negative on the left-hand side, is equal to log to the base 10 of x. So this is the easiest of the log problems to solve, because that means, by definition, almost, or maybe wholly, this means, now x is my variable, so my base is 10. That means 10 raised to the minus 7.1 is equal to x. But another way to write 10 to the minus 7.1 is simply 1 over 10 raised to the 7.1, and that's equal to x. And this answer is exact as far as we were given. But of course we can't do much with this. So in this case, what you want to do, you can do it two ways. You can actually use your calculator to get it directly right here, and that's probably the easiest, is to use just your calculator and get the answer directly right here. On the exam, I'll let you know what I want. So we want to use the x to the y button. So my button here is an x to the y, and you will probably have a button like that as well. So my x is my base, and my y is my exponent. So my base is 10, x to the y, and here I'm going to put minus 7.1. And I get the answer, and we knew it's going to be really, really, really small. And in scientific notation, how many zeros do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. With the 7, 9. So I move this 8 places over. So this is 7.9 times 10 to the minus 8. So these were 7 zeros, and I moved the decimal to scoot it right between the first non-zero number and the number right that follows. Okay. Measuring the loudness of sound in decibels. Again, another logarithmic-based scientific measurement. So the loudness of sound is measured in decibels. That's the unit. And the measurement depends on the context of an original sound intensity, symbolized by I sub 0, or I naught. Now that's going to be given to you, which corresponds to a very faint threshold of sound audible to humans. if a particular sound is measured to have intensity I, then the decibel rating of the sound is given by the formula D, which is the decibel, is equal to 10 times the log of I divided by I naught. So let's find the decibel rating of D with the sound of intensity, which is intensity I, is equal to 10,000 I naught. So it's not as bad as you might be thinking. All we pretty much need is this formula right here, and it's plug and chug. And a lot of students really like this because you feel comfortable doing things with a calculator. Somehow it gets rid of some math anxiety. So again, this is log to the base 10 I divided by I naught. So what do we have? We're wanting to find the decimal. So I'm going to multiply the log to the base 10. And what is our intensity? Our intensity, which is symbolized by I, is given by 10,000 I naught. And that's divided by I naught. How convenient, right? Since it's divided by I naught, those two cancel. So all I have to do is find the value of 10 times the log to the base 10 of 10,000. And I'm not going to use a calculator for this. I know the log to the base 10 of 10,000. All we have to do is count the zeros. That's 1, 2, 3, 4. So 10 times 4 is 40. No calculator needed. And it was much easier not to even, whip out the calculator. I just do it this way. So, I haven't talked to you about the natural logarithm. Sorry, I've been talking about the natural logarithm, and this is where it's introduced. That's the reason I didn't really want to upload 4.3 lecture from last semester, but I was behind. So let's examine this. In looking at the interest compounded daily, way back to that lecture, we encountered Euler's constant E, which the book stated was the result of continuous compounding. And we also discovered then that E is the result of what is known as taking the limit of a function as the independent variable x approaches infinity. That's the same as finding what the horizontal asymptote is in many cases. So the only difference here is we have this really close to continuous compounding formula. The difference being is that x is both in the denominator of our base and in the numerator as an exponent. So really, if we look at this, f of x, and we just call the function f of x is equal to this, as x approaches infinity, if we look at it on the graph, we can see that the value of f of x approaches a horizontal asymptote. And that asymptote is the value of E. And we've told you what that value is. If you bring up your calculator, you can find the value of E, usually because it has a value of E button. And if you put in E and hit equals, it will give you an approximation to it equal to whatever the fixed approximation is in your calculator. So here we have a new notation. It's much more natural than the log to the base 10. So ln of x, which I've already been talking about, and we call that natural log, is equal log to the base e of x. Sometimes we're lazy and we'll just say the letter is ln of x. That's what you'll probably hear me say here in fewer than 2 minutes. Sometimes we'll say the natural log of x. This is the domain. This is the graph of the natural log of x. The domain, as always, is 0 to infinity, and the range is minus infinity to infinity. Notice how quickly it changes. As soon as we get to the value of on the x-axis that's equal to e, it quickly increases without bound in the negative direction. Up here, it slowly increases. I think we can prove it is the slowest, yes, it is the slowest increasing function, continuous increasing function. It seems like that's what I learned at some point and figured out. So let's do these. So now we're going to be using the natural log, and really the natural log, or ln, is the most helpful in nature, because nature doesn't have fingers, it has math, right? So remember, ln of e to the third is equal to log to the base e of e to the third. So if that's equal to x, that implies e to the x is equal to e to the third. So x is clearly equal to 3. Let's see how that's to be done on the calculator. For the most part, as I recall, last semester when we were also doing the COVID, I wrote a final exam where you did not have to use a calculator. Because I'm assuming all of you have calculators, but in that particular class, I was already prepared for students perhaps not to have the money to go out and buy a calculator. I never know what access to funds some students have. I know I've had some students that were homeless. They were literally living on the streets. So I don't want to discriminate in that way. But in this case, we're just going to use the ln e raised to the third power, and of course we're getting 1. It's 3. What's going here? So we need to figure out how to do this. Natural log of e raised to the 3. There we get 3. So notice how important that was. So let's just think for just a second what went on here. It was a PEMDAS issue, right? When I told the computer to compute ln of e to the 3, what it did is it interpreted it to mean this. Calculate the function value of ln of e first, and then raise it to the third. Well, that's equal to 1 raised to the third, which is equal to 1. And that's the first answer we got. But in the second one, when I said calculate the natural log of e to the third, it interpreted it with the parentheses this way. So that's the reason, knowing PEMDAS and hoping like heck your PEMDAS is going to work. Here, PEMDAS is kind of ambiguous because you don't know what they're programming in. When you say ln, are they going to literally take the very next value? And then you just got to find that out. So basically, when in doubt, use parentheses. That's what I learned doing when I was doing computational math. When in doubt, use parentheses, because I cannot tell you the number of times I would have the programming right, because in computational math, some of the things that we do, besides proving things, is to write programs that will approximate answers to questions like traffic jams and the chaos of traffic jams. So when we have electric cars, we actually already have the differential equations that model traffic jams and what causes them and how to alleviate them. So if we have computer-driven cars, is what I mean to say, we can feed that algorithm in, and it will greatly reduce rush hour traffic in cities, which is kind of really cool. So here, let's just use the calculator to find the natural log of 142. And it's 4.955. And what about the natural log of this number right here? You should expect it to be negative. That's the only insight that I would want you to think about. It's like you don't know. Sometimes literally just knowing if something's positive or negative is all you need to know. And of course this is negative. I'd have to know actual powers of E in their decimal expression to even begin to estimate that. So let's go on to the next page. Oh, modern global temperature increase. This is a great one. Has to do with global warming. So carbon dioxide in the atmosphere traps heat from the sun. If you want to see a good example of that, look at Venus. I think one of the first Russian probes that landed in Venus in the 70s, they don't last very long. I think it transmits a small picture, and you can see, if you know what you're looking for, and I don't really know what I'm looking for, you can see one of the landing gears starting to melt. It's a pretty hot surface. And so carbon dioxide, we want to definitely keep it at a minimum because it traps heat from the sun and it stays in the atmosphere an awful lot. And you know, when we're burning fossil fuels, it's like we're burning ancient forests that have died and trapped all of their carbon dioxide in the ground in the form of fossil fuels. So when we're burning those fossil fuels, we are like not only burning the forest on the earth, we're burning the concentrated forest of ancient times. And that's one of the reasons this is a problem. And it's a problem, unfortunately, humans aren't very equipped to deal with, because we have to use mathematical models to see what's going to happen in the future. And that's sometimes decades down the road. And humans are more equipped to plan for 2 hours in the future, or maybe a week in the future, or sometimes a year in the future in detail. But as an entire society, planning for decades in the future is very, very hard, and it can be politically problematic. Unfortunately, the answer to that question is never to deny science, but to rather grab science by its tail, listen to it, and figure out some ways where you can have your cake and eat it too, where the economy's not harmed, but we're not also pumping tons of carbon dioxide into the atmosphere, which has been the case in an enormous measure since the industrial age. And I don't care what your political views is, everything I've said right there is objectively correct. There's really no dispute about anything I've said at all. There can't be, because the evidence for it is just as solid as can be. The arguments start is how to best ameliorate it, how to best make it better. And there are definitely issues and room for argumentation there, as anyone will readily admit. So let's read through this. Carbon dioxide in the atmosphere traps heat from the sun. The additional solar radiation trapped by carbon dioxide is radiative forcing, the difference between sunlight energy absorbed by the Earth and energy radiated back to space. It's measured in watts per square meter. So again, if you were a physicist or a climatologist or working on this issue, this would be an important measure of wattage, watts per square meter, or of heat. In 1896, the Swedish scientist Svante, I can't pronounce this, people, it's not French. You just say that word in your head however you want to say it. Modeled radiative forcing R caused by additional atmospheric carbon dioxide using a logarithmic equation. R is equal to some constant K times the natural log of C divided by C naught. So you don't know what that means, right? So you have to read down below. So R is the radiative forcing, we know what that is. C naught is the pre-industrial amount of carbon dioxide. So that would be carbon dioxide in the atmosphere before the Industrial Revolution, around the middle part of the 19th century, so like around 1850, 1860. You say, well, how would we measure that? Ice cores. We simply go to the Antarctic and drill down, and we can drill back so many years and check bubbles of gas trapped in the gas. Of course, the scientists did not know how to do that, but we know how to do that now. C is the current carbon dioxide level, and K is a constant. So many times in mathematics, and especially in physics, when we're trying to model something, we have to find experimentally what the constant K is. And the Swedish scientist, we'll call him the Swede, he discovered an upper bound and a lower bound to K. And like I said, sometimes that's the best you can do. He knew that K was between, or gave very good reasons to accept the conclusion that K was greater than or equal to 10, but less than or equal to 20. So that allows you to calculate error bounds. If we assume K is equal to 16, this is the result. If we assume K is equal to 10, this is the result. So the real answer is going to be somewhere in between these two extremes. It's probably not the best error bounds we would like, but it's something. And later on, when we get more sophisticated techniques, we can reduce the error bound. So this is the error, or the value of K, discovered by the Swede in 1896. I'll guarantee you, we know it much more accurate now. And we're assuming that the value of C is 2 times C naught. In other words, he was able to establish blah, blah, blah. So let C be equal to 2 C naught. Is the relationship between R and K linear or logarithmic? So let's do that right now. You think, how am I going to answer that question? Linear scales versus logarithmic scales. If you're a COVID-19, if you like data and you like to follow that, COVID-19 grows exponentially. But many of the graphs that you're given don't use the regular scale. They use a logarithmic scale for the x and the y. So if you see, for example, let me just talk to you about this really fast. If you're looking at a Cartesian graph, and I'll just do this along the y-axis, and this is 10, this is 100, this is 1,000. It's going up by powers of 10 each time. So that indicates a log scale. So that means logarithmic functions look linear. So if you have a scale, a graph scale that is log, then a logarithmic function, a function that grows, then an exponential function, a function that grows exponentially, looks linear. And many people, when they look at COVID-19 growth, the scale is a logarithmic scale. But it looks like it's just a linear growth, and they don't realize that it's logarithmic, and they make some really bad errors in what they state. That's the reason you need to have people who know what's going on and listen to them, and then start studying it yourself. So what are we being asked to do here? So what is the relationship between R and K? So we're going to do R is equal to K times the log. C is equal to 2 C naught over C naught. So this is not going to be so hard. So R is equal to K times log of 2, natural log of 2. So let's find the natural log of 2. First, let's think about this. The natural log of 2 is a constant. So let's put this in a more familiar landing. So R is equal to K times some constant C. So this is a Y is equal to a constant times another constant, which is Y is equal to some constant. Can you give me an example? Think about this. Y is equal to 20. That's a constant. What is the graph of Y is equal to 20? It's a line, right? What type of a line is it? It's a horizontal line. So this is linear. Why? Because K is a constant, and it's not a variable. We don't know what it is, but it's some constant. And the natural log of 2 is another constant. And I'm treating my R is my dependent variable. That's the reason I related it to Y. So it's just simply, in other words, here would be my R axis. And here would be my 2C0 axis or something like that. Anyway, the answer is it's linear. Not only is it linear, it's horizontal. So here's the interesting thing. If you're looking at an exponential function with a logarithmic graph, so logarithmic scaled graph, and the graph is a horizontal line, that translates when I replot that using your regular Cartesian coordinates where the scale is not logarithmic, what I'm going to get is a straight line function. It won't be horizontal though. Let's go on. Log, I mean, this is really where math gets so interesting. The discovery of logs and the natural log has completely changed our view of the world. So here we have TR is equal to 1.03 R. Right, TR is a function of K. So first note, what I want to show you here, this is like Tx is equal to 1.03x. And you know that would be the same as y is equal to 1.03x. So you know on the regular scale, the scale you've already used, this is going to be a line with a positive slope that goes straight through the origin, and would look something like this because the slope is just barely over 1. So it's very, very close to the line y is equal to x. But they want us to write TR as a function of k. So let's go ahead and do that. TR is equal to 1.03. And what is R equal to? Well, R is equal to K times the natural log of C over C naught. And that's T sub R is equal to 1.03 times K times log of C over C naught. And this will be a fixed number too. And that's all you have to do for that one. It was pretty simple. So now let's go on to the change of basis theorem. So we've been given the log to the base 10 and log to the base e. Suppose I want to know log to the base 2. That's really important in computer science. I need to know the calculation of something log to the base 2, or maybe log to the base 16, or maybe log to the base 32 in computer science. Well, guess what? We have a change of base theorem. So the log to any base a of some number x is equal to log to the base b of x divided by log to the base b of a, where b and a are not equal to 1. So I'm able to choose my base there. So you just choose a base. So I'll just show you how to do this with 2 examples. How is that? So I want to find log to the base 5. And we don't have that on the only way I can find log to the base 5 is to use the change of base theorem, because I only have log to the base 10 and log to the base e. But I want to know what log to the base 5 is. Indeed, many times I want to know myself personally what the log to the base 2 is. So log to the base 5 of 17 is equal to log to the base b of 17 divided by log to the base b of 5. So my a value is 5. A is equal to 5. X is equal to 17. B, we choose. So if you want, you can choose log 5 to the base 5 of 17 is equal to the log to the base 10 of 17 divided by log to the base 10 of 5. Or if you wish, you can choose another base, log to the base 5 of 17 is going to be equal to the natural log of 17 divided by the natural log of 5. And we'll show that we get the exact same number. So what I have to do is clear out everything. I'm going to calculate the log to the base 7 of the log to the base 10 of 17, and I'm going to divide it by log to the base 10 of 5. Notice I put the parentheses there because I don't know what it's going to do. And I get 1.76. So that's approximately equal to 1.76. Now let's use, instead of log to the base 10, log to the natural log, log to the base e. Clear out. So now let's take the natural log of 17 and divide it by, I'm going to put parentheses there, the natural log of 5. Probably don't have to put parentheses there, but I don't know. And I'm going to get 1.76. Same answer. So you get to choose the base. I would say choose 10 or choose E. If you choose 10, that means you use the log button. If you choose E, you use the ln button. And that's all there is to it. So now let's find out what is log to the base 2 of 0.1. Well, let's use ln, the natural log. ln of 0.1 divided by the ln of 2. So the log of 0.1, so I know 0.1, so I know, let me put the leading 0 in there, okay, for so those of you who are used to leading 0. So I know that the log of 0.1 is going to be negative, right? So the answer is going to be negative, divided by the natural log of 2. And I get my answer, and indeed it's negative, minus 3.32. And this is approximate. This is exact. This is approximate. Of course, with the exact, there's not much I can do with it. Okay, so this is a really interesting mathematical experimentation. So listen, I'm going to put this up here for you all to do as extra credit. And you will want to use your calculator. If some of you know how to code, you can code it up as well. So suppose you're studying an ecological system with a total of 1,000 animals. There are 3 different species of animals whose populations are P1, P2, and P3. One measure of how diverse in terms of species that system is can be obtained by the following formula. Notice the whole thing is included in parentheses, and it has to deal with log to the base 2. So it's my population 1 divided by 1,000 times the log to the base 2 times that population divided by 1,000. Then I do the population of, there's 1,000 animals. The population of my species 2 divided by 1,000 times the log to the base 2 of the population divided by 1,000. So you're taking the log of this number, my population divided by 1,000, plus the population of my third species divided by 1,000 times log to the base 2 times the population divided by the 1,000. And H is, and then once you add those 3 things up, you change their sign, because right there's the negative at the very beginning. So H is a measure of diversity, and H is clearly bound above by log to the base 2 of 3, and bound below by what? What is the range of logs? Well, it doesn't have a lower bound. So what I want you to do is to experiment with different values of P1, P2, and P3. Well, it doesn't have an obvious lower bound. I want you to experiment with different values of P1, P2, and P3 so that you find a value of H between 0.95 and 1.05. And this may very well be a take-home segment of your next exam. So here's some more help. Notice that the values of P1, P2, and P3, whatever you choose, they have to add up to 1,000. The sum of the individual species populations have to add up to the total population. So suppose my species are rabbits, coyotes, and wild turkey. And I say, well, there's 50 rabbits, 750 coyote, then the population of my wild turkeys has to be 200, because the total has to add up to 1,000. So one of the easiest ways to do this is just to come up with 3 numbers, P1, P2, and P3, the total to 1,000, and check the H value. If that doesn't give you an H value between 95 and 0.95 and 1.05, then change one of the H values, raise up one H value by 10, and subtract it from another, and calculate again. Each time you have to check that all of your numerators, or all of your P1, P2, and P3 values add up to 1,000. It's a calculator computer-based experiment. If you know how to code, you can do it up in code, but I will want to see your code. And I want to give some assurances that you actually coded it up. So this will probably be given to you as a take-home part to your next exam, or I will give it to you as extra credit.